All right, guys, it's been a while since I've last made a video. Today I'm going to be doing problem of the day for December 28th. This is 1962. Remove stones to minimize the total. I have not attempted this problem before, so we're going to go ahead and get started. It says you are given a zero-indexed integer array piles, where piles I represents the number of stones in the ith pile and an integer k. So you get two parameters, okay? So you should apply the following operation exactly k times. You should choose any of the piles I and remove half of the pile stones from it. Okay. Notice that you can apply the operation on the same pile more than once. Return the minimum possible total number of stones remaining after applying the k operation. So floor division is saying remove the floor division 2 stones from it. So if I, for example, have 5, 4, 9, and I'm going to remove half the pile, half the stones in a pile 2 times, I would start with the 9, and 9 floor division 2 is 4, so I remove 4 stones, and then again I remove floor division 5 here and 3. Here, you used to remove a so you can either start with the 6 or the 7. It doesn't really matter because you're only going to remove 3 stones at most. So you move 3 here, and right, 2 and 4, and so then you remove the 6, half it, the 7, half it, and then the 4 again, half it. Okay, so there's a pattern here. But before we get that, let's formally write out our goals and inputs. So as stated before, goal, return total number of stones after k removal operations. A removal operation is removing floor division 2 stones from a single pile. Inputs, we have param 1, which is stones in each ith pile. Param 2, number of removal operations to execute. Output, return the total number of stones after k, after k removal operations. Okay. Now the pseudocode, we did note here, each step, remove the pile with the most stones in it. Right? So in that case, five, 4, 9, k equals 2. So we need to remove the pile with the most stones in it in each step. That means we need to get the maximum. So how do we do that? Well, you can do a linear search for maximum. So that's O of n time. Every single time you look for the maximum. And you do that k times, so that's O of n times k times complexity. So I search for the maximum k times, and that takes O of n times k times complexity. We could do a binary search after sorting, so that's O of n log n time, and that's not exactly faster, so to say. Log n could be greater than k, and most likely is. So another thing we could use, a data structure we could use to find the maximum element of an array, any k times, you're going to look for a heap. Now the time complexity for this is pretty interesting. Inserting n number of elements into a heap takes n log of n time, because each insertion takes log n time. And you do that n times, so n log n. But if you heapify an existing array already, and you don't have to reallocate space or anything like that, and you can kind of just you do this bubble up algorithm, right? So you bubble the maximums up, and that's O of n time complexity, essentially. So if we use that, we use a heapify, it should ideally be pretty fast. So we'll use a heap, we'll heapify the piles array. And then after that, we will pop the largest one, floor 2, and then re-add it to the piles heap. And you repeat that k times. So that's actually O of n time for the creation of the heap. And we will have k log n times of removing and inserting and deleting and flooring. And of course another O of n, execution to get the sum at the very end after removing all that. So what have I done? I've stated my goals, inputs, outputs. I walked through the pseudocode, some heuristics we can use, and now edge cases. So according to these constraints here, we'll always have at least one pile, and we'll always execute at least one K. So with that in mind, edge cases probably won't have to think about too hard. Now, is there any tricky parts with the floor division? And I'm thinking not really. Here it says you should divide the 6 before the 7, but it really doesn't matter because you're removing the same amount of stuff. So ideally, you still want the maximum number. Okay, so let's implement this. Let's go ahead and clone the piles into an array P, and then we're going to go ahead and heapify this. Oh, space complexity. Before I move on, space complexity of this is going to be O of n, because you have a heap of size O of n. Okay, so now if I recall, for Python, it's going to be heapify, heapq. Now heapify p. And then we're going to say for blank and range k, we are going to do, actually, we'll need negative values because this is a max heap. So negative x for x in piles. So make it negative. Now we're going to say for every operation we need to pop our number, our current pile, and we're going to say heap q dot heap pop p. We're going to say cur is equal to negative cur floor 2, or we say negative cur minus, so it's equal to example if our cur is 7, so it would be negative. Oh, let's do this. This will be easier to understand. Okay, so it's 7. So 7 minus 3 is going to be 4. So that's our new element to insert. And we're going to say heap q dot heap push onto p dot current. And return the sum of p. Or p is equal to negative x and p. Actually, are there any numbers negative? No. So return negative sum of p. This is negative. Okay, so just like I said, we have our heap. We create the heap using the heapify. So it's O of n time complexity. And then we simply do our removal and re-adding onto the pile. So we run this. This should be our correct answer. So usually at this point in the interview, the interviewer would ask, are there any more test cases you could create? And certainly I could. Of course, you could go with the single case, go with the large number, and of course maybe something more complicated where you have repeated digits. Okay, and that should be it. Now, before I go ahead and submit, this is also the point in the interview where you be asked, are there any more optimizations you could make? And here I'd say, okay, well, one, I wouldn't clone the variable to save on space. You can get O of 1 time complexity if you just use the array that's passed into the parameter. In Python, it's passed by reference. So it's not actually, you're not copying any values, especially when it comes to list. As far as the time complexity goes, I think a heap is going to be the fastest. Now the question is, do I need a heap of size n? Can I get away with the heap of size k? And to that I answer probably not. Maybe I was thinking you can get away with a heap of size 2 times k. So for example, the biggest 4 elements here, or the biggest 6 elements here. Because, well, if you remove, I can't off the top of my head think of a case. Well, better safe than sorry, right? There is a case where even if you have a heap of size 6 and this is size 1,000, right? That probably, the 6 largest numbers may not be enough. So let's go ahead and submit it, and let's see if the solutions, if I missed any test cases. So I beat 95%, and in memory beat about 26%. Let's take a look at the solutions that other people have done. Lead215 is a great resource if you ever see him or her on the answers. Go ahead and give them a look. They usually have a very, very pretty and short answer. Okay, so it says here heap.heap replace a 0 to 2 thing of some a. So that's essentially what I've done. And they said the time complexity is n plus k log n, just like I said. Okay, so that's it for today. Thank you for watching. Make sure you comment down below. Let me know what I can do to improve. And yeah, I hope you were able to learn something from this.